Hi everyone, I'm Masoud Agassi, and in this video series we are going to learn about processes and threads. Whether you are new to this topic or want to understand it better, this series will explain everything in a simple and practical way. Let's get started. In previous parts we learned about the definitions of processes and threads in the context of an operating system, process scheduling policies and the steps involved in a context switch, the most important challenges of concurrent programming that every software developer should be aware of, and the best practices for utilizing threads in Java. In this part, we will explore some of the best practices for addressing concurrent programming challenges in Java. Most concurrent programming issues arise when sharing data between threads. One way to avoid this issue is to simply not share any mutable data, which is called thread confinement. There are several ways to implement thread confinement. Let's examine them with an example. This Java class has an isPrime method that is called by multiple threads to check if a given number is prime. While the method must be thread safe, the isPrime variable at line 9 is totally thread safe because it exists only in the caller thread's stack memory and it isn't shared with other threads. This technique is called stack confinement, where objects are accessible only through local variables. Now let's consider storing prime numbers in a database. Assume we already have a DB connection class that is not thread safe and holds a connection to database and provides methods for common database operations. One way to achieve this is to create one instance of DB connection or a pool of a few DB connections and share it with all the caller threads. But DB connection class is not thread safe, and in this case we need to handle the synchronized access to the DB connection instances ourselves. What if each thread could have its own instance of DB connection? In this way we don't share the DB connection instances between threads, so no synchronization is needed. And also we will have enough instances of DB connections that no thread need to wait for other threads to finish their work. We can use thread local to achieve this. Thread local is like a variable that holds per thread values. Let's implement this solution. First, we need to create a thread local object for the DB connection. The initial value method of the thread local will create a new instance of DB connection for each thread when needed. Then we need to call the insert operation inside the isPrime method. Now each thread has its own instance of DB connection and we are not sharing any data between threads. So far we have learned that thread confinement helps us to not share any data between threads. But even in cases that we need to share data, it's still safer to share immutable data. Because most of the concurrent programming challenges that we have discussed so far happen when multiple threads access the same modifiable data at the same time. Let's see how we can leverage the power of immutable objects in our code. Let's say that now the isPrime method needs to return an object instead of a simple Boolean value. We already have a class definition for this return value called primeResult. PrimeResult has a simple definition. It has three data fields which are the given number, the result of the isPrime check, and the processing time in milliseconds. And then it has a simple constructor and getter-setter methods. Now let's update the isPrime method to return an instance of primeResult. But there is an issue with this implementation. Our program is a multi-threaded program and the result of the isPrime method could get shared between multiple threads. The current implementation of the primeResult class is mutable. Fields can get modified by multiple threads at the same time, so primeResult is not thread safe. In this case, we can make the primeResult class immutable to avoid atomicity and visibility issues of shared data. In order to make the primeResult class immutable, we have to make all the fields final and remove the setter methods, or simply change the class definition to a Java record class. Awesome! Now the prime result class is immutable and thread safe. Generally, it's a good practice to keep classes and variables immutable by default unless the opposite is needed. Until now, we have learned how to not share data using threads confinement techniques and also how to share immutable data to avoid atomicity and visibility challenges. But what if we need to share some modifiable data between threads? In previous parts, we have seen how we can implement synchronization logic ourselves, but Java provides concurrent implementations for many types and data structures, and it's a best practice to use them when possible instead of developing our own synchronization logic. Let's review some of these classes and their use cases. Sometimes we need to share a single primitive type variable between multiple threads. Java already provided some thread-safe implementations for this use case under the Java Util Concurrent Atomic package. In previous parts, we have seen the use of atomic integer class, but there are other atomic classes to use as well, such as atomic long or atomic boolean. But what if we need to share data structures such as map, list, or set between multiple threads? Java also provides some thread-safe concurrent implementations for these data structures. We can find them under the Java Util Concurrent path. For example, concurrent hash map is a thread-safe map implementation and provides map operations plus some new operations in a thread-safe manner. Another concurrent data structure is copy-on-write array list. This is a thread-safe immutable array list implementation that copies all its data to a new array on each modification. It brings a performance overhead in use cases that require a lot of modifications, but is a good match for use cases that need iteration over items more than modification of the collection. There are other collection types in this package as well, such as copy-on-write set, that I recommend you to check later. It's generally a good practice to use these thread-safe types and collections when needed, instead of developing your own synchronization logic. In previous parts, we learned about the synchronized block, which is a synchronizer. A synchronizer is simply an object that controls the execution of threads based on its state. There are other synchronizer classes in the Java library that could be handy in specific situations. Let's briefly review some of them. In this example, we review the usage of the countdown latch synchronizer. A latch is a synchronizer that can delay the execution of threads until a specific state is reached. And the countdown latch is a latch implementation that allows some threads to wait until a set of events occur. Its constructor receives the number of events to wait for. Whenever one of the events occur, its countdown method should get called, which decrements the event's counter. From the other side, the await method waits for the counter to reach 0, which means all the events have occurred. Now let's review the code. We first create a countdown latch with event counter value of 3. Then we create a fixed pool of 3 threads, and after that submit 3 tasks to this pool. After that, we call the await method of the latch, which waits for the event counter to reach 0. Then we shut down the executor. Inside the worker runnable, we first simulate some time-consuming task, and after that we decrement the latch counter by 1 through calling the countdown method. In this way, the main thread waits for all the 3 workers to finish their job before exiting the program. Semaphore is another important synchronizer object. Semaphore behaves like a permit holder for a concurrent service. For example, in this program, we have a printer that can handle only 2 print jobs at a time. So first we create a semaphore for this printer with permits value of 2. Then inside the print method, we first try to acquire a permit using the acquire method. If no permits available at this point, our thread blocks here until a permit becomes available. Otherwise, if any of the two permits are available, we quickly acquire it and move on. After acquiring the permit, we simulate the print job and at the end we release our permit. Inside the main method, we first instantiate the printer and then create 5 threads to do the print jobs concurrently. In this way, the semaphore protects the printer by allowing only 2 print jobs at the same time, and next jobs have to wait for previous jobs to finish to get their turn. There are other types of synchronizers inside the JavaUtil concurrent package, such as the cyclic barrier, that we don't have time to cover them in this video, and I recommend you to check them later. Thanks for watching part 6 of this tutorial series. In this part we explored some of the best practices for addressing concurrent programming challenges in Java. In the next part we will have an overview of modern frameworks and innovations in the realm of Java concurrent programming. If you found this video helpful, don't forget to give it a thumbs up and subscribe to the channel for more tutorials like this. It's going to be an exciting journey, so make sure to stay tuned.